like piecewise functions. These get their name because they're defined in pieces. They typically look something like this. For this one, f of x is equal to x squared whenever x is less than or equal to 1. And f of x is equal to 2x plus 1 when x is greater than 1. So if I wanted to evaluate something like f of 0, 0 is less than 1, so we're going to use x squared. 0 squared is equal to 0. For f of 1, 1 is less than or equal to 1, so we'll use the first equation again. 1 squared is 1. However, for f of 2, 2 is greater than 1, so we're going to use our second equation, 2 times 2 plus 1, which is equal to 5. Let's look at this function a little more in depth, in particular, the graph. Typically for a graph, we pick some numbers for x and solve for y. But this time, I'm going to need to essentially do this twice. First, for x squared. For x squared, we specifically need x to be less than or equal to 1, so I'm going to check numbers -2, -1, 0, and 1. We don't want to go past 1 since we need x to be less than or equal to 1 for this problem. -2 squared is 4, -1 squared is 1, 0 squared is 0, and 1 squared is 1. I'm then going to do another table for 2x plus 1. And this time I need numbers bigger than 1. So numbers like 2, 3, and 4. And even though I'm not supposed to plug 1 into the second equation, we still need to check it. It won't be on the graph, but it's still going to be important for us to know where that point would be. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. And 2 times 4 plus 1 is 9. I'm now going to plot these points and connect the dots. When I plot these, I have -2, 4, -1, 1, 0, 0, and 1, 1 for the first group. The second group, remember 1, 3 is technically not on the graph, but we do have 2, 5, and 3, 7. 4, 9 is off of the current picture I have here. But this value of 1, 3 is going to be important in this graph. In particular, we can see that point right here at the end of the line segment. We typically draw an open circle. The open circle tells me that while that point is not technically on the graph, we can get really, really close to it. I'm not supposed to plug 1 into that second equation because that only works for x greater than 1. But I could plug something like 1.00001 in. So we can get as close to that point as we need to, but never actually touch it. And for this, we use this open dot. Next, let's look at the function f of x is equal to the absolute value of x. This doesn't look like a piecewise function, but it is. For this one, if we use positive x values, we would just output the same number. The absolute value of a positive number is just that number. So f of x is equal to x as long as x is greater than or equal to 0. However, when we input a negative number, we're going to change the sign, and we represent that by writing -x. Since x is negative itself, I would have negative x, which would make it positive again. To graph this, I'm going to plug in values like -2, -1, 0, 1, and 2. The absolute value of 2 is 2, the absolute value of 1 is 1, and the absolute value of 0 is 0. All three of those get plugged into the top part of our piecewise function, which just outputs the same thing. For -1, since -1 is less than 0, I would have negative -1, which is 1. For -2, I would have negative -2, which is 2. I can plot these points, -2, 2, -1, 1, 0, 0, 1, 1, and 1, 2, and we can connect the dots to see that this graph looks like a V. Next, let's look at a very important piecewise function known as the greatest integer function. The greatest integer function is denoted by these kind of half square brackets. They only have the bar on the bottom. It is the largest integer that is less than or equal to x. So for an integer like 3, the largest integer that's less than or equal to 3 would be 3. If I wanted to look at something like 3.2, I want an integer that's less than or equal to 3.2, but it's the largest possible, which is 3. If we had something like 2.999, the largest integer that's less than or equal to this would be 2. For something like -0.5, we need to be smaller than this value, but still an integer, so -1. And for something like -4.8, we would go down to -5. So we can think about this as always rounding down. This is what the graph of my greatest integer function looks like. It's sometimes known as a step function because it looks like steps. If we were to take the floor function or the greatest integer function of 1, we would get 1, which is denoted by this point here. For any number between 1 and 2, like 1.2 or 1.7, I would output 1. And that works for any number between 1 and 2, and that's represented by this horizontal line between 1 and 2. When I do 2, I would get an output of 2. So at that point, I would jump up to an output of 2. And so we leave an open dot at the point 2, 1 because it doesn't actually hit that point. It just gets as close as we possibly can.
If you would like to see Professor Pierce make more videos like this one, you can support her on Patreon in the link below. Any and all support means a lot to her. It allows her not only to make more videos, but it also allows her to campaign for free and accessible online education to conferences and other universities. Thank you for watching, and remember, math is for everyone.